morning. Today is Wednesday, the day before Thanksgiving. We have an extra half class to make up for the half class that I owed you. So we're starting a little early today. So we'll have 1.5 classes. Again, please feel free to interrupt, to ask questions. Let me start by making comments on the exam. I'm almost done grading the exam. I graded problems 2 and 3, which are the long problems. Problem 1 is the short problem. I left the easy one for last. So I should be able to finish that today, but I'll give them back on Monday, all the exams. Okay, so problem 1 was a little mathematical. I didn't grade that one yet, so I have nothing to say about that. But problems 2 and 3, I do have something to say about. Problem 2 involved writing. The first thing you had to do was write energy balances on 2 reactors. One that was heat exchange, one that just exchanged heat, and the other one that had a zeroth order reaction. Most of the class could not write energy balances on these 2 systems correctly. I'm not talking about solving the problem. I'm talking about writing an energy balance. There were at least 5 people who just wrote mass balances. Didn't even write energy balances. There were also a number of people that didn't realize that since you have 2 reactors, you need a separate balance for the first reactor and a separate balance for the second reactor. So there was only reaction in the second reactor, and some people put the reaction in both reactors, or they put the heat exchanger in both reactors. That goes back to 228, how to write an energy balance. If you have 2 reactors, each one gets its own balance. The first reactor had a heat exchanger, the second reactor had a reaction. When you do an energy balance, every term in the equation has to have the same units. When you do any balance, any equation, every term has to have the same units. Some people in the energy balance just put a reaction rate in. But that's in units of moles per unit volume time. And the rest of the equation was in units of energy per unit time. So to get from moles per unit volume time to energy per unit time, you have to multiply by energy per mole minus delta H times volume, which is the volume of the reactor. So units are important. You can't have an equation where different terms of the equation have different units. Doesn't make sense. So that was very disheartening, because in this class, it builds on your material and energy balance classes. How can we talk about putting control in an equation and solving an equation if the basic equation, the mass and energy balance, in this case the energy balance, if 2/3 of the class can't write an energy balance? So here I'm talking probably at least as much to the people on camera as the people who are here, because I have to say I noticed a lack of commitment on the part of many students who don't show up. In almost every class, there are at least 10 people missing. At least 10 people who don't come. The people who are here, that's great. And the faces I see here, I usually see at all the classes. But the faces who are not here, many of them frequently are not here. And, that's not a way to really learn the material. It's not an easy class. So it requires some commitment. Problem 3 was also problematic for a different reason. Problem 2 was problematic, that is, the responses to problem 2 were problematic because they relied on people being able to write energy balances from 228. Problem 3 was problematic because I gave that problem for homework. The TA solved that problem in the recitation, which was recorded and posted for everyone to see. Yet, more than half the class didn't get many points on that problem. 3A was a homework problem that was solved and recorded. Now, obviously, I went around trying to make sure you didn't bring along solutions from homeworks to copy, but you were supposed to study for the exam. I'm talking to the camera. No, it's okay, you don't have to. I'm not just talking to the people in the room. I don't look at the names. Difference there was the error. And then the error went into a controller which outputted a manipulated variable. And that went into a final element, or a valve, typically. Which then went into the process, GP. And in parallel to that, I could have a disturbance and the two of those together gave me the control variable, which I might have to measure. It's not obvious, so I have a GS for the sensor, and that gives me a CV prime. So that's the feedback control diagram, block diagram. And we had a result, which we did, which said that CV prime tilde was equal to something times ST prime tilde plus something times D prime tilde. And here I had a GD, and here I had a GP, GV, GC. And here I had, I'm guessing, I'm going to have to look this up. I think I had a GS, GP, GV, GC, GS, GP, GV, GC. And then I'd like to check, because I don't feel like rewriting it. GP, GV, GX. That's correct. And 1 plus GP, GV, D, GC, GS. Yes. Okay. Miracles happen. I got that right. And we spoke about different controllers, and we decided we wanted to have a GC, which for a PID controller, PID, proportional integral differential, looked like this. We had a KC times 1, that was the proportional part, plus TI, STI, S over TI. That was the integral. And then I had plus STD, differential. Where this said that the proportional said that M V prime tilde was KC times, well actually let's, without the tilde, was KC times E of T. And this was KC times the integral E of T prime T prime divided by Ti. And this was Kc times d E dt times Td. Where E was the difference between SP and CVF. So this is all just review from your notes. So this was the proportional part, this was the integral part, and this was the differential part. Where we looked at them one at a time. Just proportional, just integral, just differential. And notice that each one has a parameter. So I've got Kc for the proportional. I've got Kc over Ti, so Ti controls the strength of the integral. And Kc Td controls the strength of the differential. And this way I can adjust them independently. And when you use Simulink, you can actually plug in and use these and see the effect. Let's just notice some units here. The units of GP, or the units of GP, the unit GP usually involves a KP. KP is inside the steady state gain. So notice the steady state gain has units of a control variable over a manipulated variable, or GPGV. So KP comes into GPGV, and it has units of the control variable over the units of the manipulated variable. Let's notice that GC also has a K in it, KC. That's in GC. And let's just notice that the output, it's the units of manipulated variable divided by the units of the error. Well, the error is the difference between the set point and the measured control variable. And the control variable measured presumably has the same units as the control variable. So it has units of the manipulated variable over the control variable. So KP and KC have inverse units. So if I multiply them together, I get something that's dimensionless. So that's something to recall. Now, we worked out two canonical examples, and I just summarized the results here on a page that I photocopied up so that you would have this as your reference instead of me writing it on the board 1,000 times. And this way, you would have it handy, so you wouldn't have to look at it. Now that, of course, presupposes A, that you're here, and B, that you actually bring this to class. This is for that group up here. There you go. Sure. Of course, those people who wouldn't be bothered to come to class will have to pick this up some other time. That's for her in a second. Okay, so we had two canonical examples, and those are the ones that we've been testing things out on. So when I say canonical, I mean these are the examples we keep on going back to. So if you look at the page, there are two canonical examples. So one of them was the 3 CSTRs in series. One, two, and three, where we would measure the concentration of the output, and if we don't like it, we could adjust the flow here. This is VA of XAA. Here we have VB XAB. Where you can note that we said that VA is much, much less than VB, but XAA is much greater than XAB. And the point of this process was that if we don't like what's coming out in the output, we can spike the feed. So the disturbance, GD, or why do we say the disturbance variable, well, the control variable in this case is XA3, what comes out here, XA3. The manipulated variable is VA. And typically there's a disturbance, at least in this case, there's a disturbance to XAB. And what we have on the sheet here, which I'm not going to copy, is based on this, I calculated GP and GD. So I have GP and GD, and they're listed here. And they're both of the form of something here, KP over 1 plus ST, and this is a KD over 1 plus ST. And I have the derivations right here on the paper. I'm sorry, 1 plus ST cubed. Where I have the details of what KP and KD are. In this case, KD is 1, and KP is something else. And the second canonical example is the energy balance one. So the second canonical example was one I worked out last time. So here I have a theta in, temperature in. Here I have a theta out, which is the same as theta. And of course I measure theta, and I measure theta. And if I don't like it, I change the coolant flow. So the coolant flow I have VC. And in this case, the control variable is equal to theta. The manipulated variable is VC. And there could be a disturbance to, I also have a V in, which I assume is constant. And I have disturbance to theta in. So if I don't like theta out, I can adjust the coolant flow rate. If theta out is too hot, I can make less coolant. If I have theta out is too cold, I can have, if I have theta hot is too hot, I can increase the coolant flow. If theta out is too cold, I can reduce the coolant flow, etc. And here again, I calculated GP and GV. And they both had a KP over 1 plus ST, KP, and GD over 1 plus ST. And I calculated KP and KD for both of these, and they're on the sheet. Okay, so I don't need to really repeat any of that. You can just look at your sheet. You have that in detail. And I derived both of these in class, so that's just the way it is. And the page just summarizes that. And what we'd like to do is we would like to examine, or what we've been doing, is we've been examining the performance of a controller that's just proportional, or just integral, or just differential, just only one of these, for these two canonical examples in this control loop. And of course, in order to do that, I need to know all 4 of these G's. So typically in these canonical examples, I assume that KV is just a constant, which I can choose units to make that constant 1. And I assume that GV. And I assume that GS was just equal to 1. These are assumed. They don't have to be that way, but that's the way I did in these examples. And what I'd like to do now is look what happens when I combine these, because we said there were pluses and minuses to each controller. We said, for example, that for the proportional controller, it was pretty fast. It lowered the time scales, but it could make the system unstable. And in addition to making it unstable, it also never gets rid of the offset. So it has good and bad. It's like with people. There's no perfectly good and no perfectly bad. They have good points and bad points. The good points is it gives you a speedy response. Bad points, you could overdo it, and it doesn't get rid of the offset. The integral gets rid of the offset. That's the really good thing. The bad thing is, again, if it's too aggressive, it can make things unstable. But even if you don't, it takes forever. It takes a long time. It's sluggish. The differential anticipates. It has a good thing is it doesn't wait for the error to get big. If things are starting to get bad, it sees that before they get really bad, and tries to head it off at the pass to correct it. The problem is it's super sensitive to fluctuations, to small fluctuations. And it can do really bad things because it can mistake little fluctuations for trends that are not trends. So we have to be very careful with this. Another question is, what happens when we put them together? So what I'd like to do is I'd like to put them together for example 2. That's the one I want to do. And let's do that for, what situation do I have? Just proportional integral control. So let's look at this canonical example for PI control. So I'm going to leave out the differential right now. And I'm going to use the second canonical example. And I'd like to do it for, I think, a change in SP, right? Or a change in D. Yeah, change in SP. PI control, SP prime non-zero, D prime yes. So that's the example I'd like to do. All right, so that says I need this part of the equation because D prime is 0. And let's look at CV prime. See, that's GP, GV, GC. Okay, GP is KP, and GV I just assume this constant is 1. So GP, GV is just KP over 1 plus ST. GC for proportional integral is KC times 1 plus S over Ti divided by 1 plus GS, which is 1, GV is 1, and GP, GC is whatever I had up here. So I've got KP, KC, 1 plus ST, 1 plus S over Ti. And this whole thing gets multiplied by SE prime total. Is that clear? Yep.
You put GP, which is KP over 1 plus ST. So what happened to the KC? The GC, sorry, because you wrote 1 plus S over
GC is KC times 1 plus S over Ti.
What about the gap?
Yeah, I just said we're going to do PI control. So this is PID. Right now, I'm going to start just with doing 2 of them, not 3. I can put the third one in, but I want to start with an easier example. Before we were doing 1 at a time. Now I want to do 2 at a time. We'll do 3 at a time. Don't worry, I didn't forget. Okay, so let's look at this thing. Let's multiply it out. So I have this is so in order to multiply things out, I'm going to multiply by 1 plus ST. So I've got KP, KC times 1 plus S over Ti. And do I want to multiply out the Ti too? I don't have to, but yeah, let's multiply out the Ti as well. What? I'll see when I get to it. Okay, so this is 1 plus ST plus KP, KC times plus KP, KC, S over Ti. And let me multiply this one out too. So plus KP, KC, S over Ti. And to make this a little simpler, I'm going to divide through by KP, KC, top and bottom. So here I have 1 plus S over Ti. Divided by, let's see, so here, did I lose an S? That looks okay. You know, this should not, the S should have been in the denominator. Sorry. Yeah, the S should have been, because it's an integral. The S should be in the denominator. I do something as well. This is 1 over SPI. So to get to the next step, okay, so to get to the next step, I'm going to multiply through by STI. So STI over KBKC divided by STI over KBKC. So in the numerator, I'm going to have STI 1 plus STI. Because when I divide by KBKC, this drops out, and I multiply STI, this becomes a 1. And this just becomes STI. Divided by okay, and so now when I multiply by STI, so this term becomes S squared times TTI. That's this term. And now I want the S terms, plus S times. So I'm going to have 1 plus KBKC. So this is equal to S times TI times 1 plus T, let's see, 1 plus 1 over KBKC. Did I get that right? STI over KBKC, that's the 1, plus STI, that was correct. And so that takes care of these two terms. And all I'm left with is this term, which is just 1. So notice I have a quadratic here. Okay, and I still have the, this is multiplied by SP prime total. SP prime total. Okay, so in order to analyze this, we need to look at the denominator, the roots of the denominator. So if we want to look at the stability. So let's look at the roots of the denominator. Well, notice that this looks like, this is a quadratic, and we want to compare this with the standard form of the quadratic that we analyzed in the past. So let's compare the denominator with S squared times T2 squared plus S times 2C T2 plus 1. That was the standard form for a second order system. So, well, the ones look the same. And notice this tells me that T2 is just TTI square root. Because T2 squared was equal to this. And C should be equal to this thing. So it's TI 1 plus 1 over KC divided by 2T2. Divided by 2 square roots of TTI. And we could simplify that a little bit. C is equal to, so I've got a 1 over 2. I've got a 1 plus 1 over KC. And I have the square root of Ti over T. So that's C. Okay, and so what do I want to do there? I would like to, let's just make sure I haven't made any mistakes. That looks okay. Okay, so the first thing to notice is that C is greater than 0 because it's 1 plus a positive number over 2 times another positive number, so it's greater than 0. So that's the first thing that's positive, and obviously T2 is greater than 0. But what we don't know is if this is greater than 1 or less than 1. So let's recall for the general form that the roots S1, 2 were equal to minus C plus or minus square root of C squared minus 1 over T. T or 2T? Over T2. So that was what we had earlier. So notice, this thing, when I'm in this form, the minus C is always bigger than the square root. So these are both always going to have negative real part. going to have a negative real part because this is c squared minus a positive number. So the magnitude of this is less than c squared. So when I take the square root, the magnitude is less than c. So even when I add it, I can't overcome the minus c here. So therefore it's stable. But if c is greater than 1, it's overdamped. Meaning this is real because it's positive, so therefore just as an exponential decay. But if c is less than 1, it's underdamped. Meaning it oscillates and decays. So those are things that we recall, and we can notice that we obviously know that c is positive. And a and c, a is t2 squared, and c is 1. So they're both positive, so this thing is negative. But I don't know if this is greater than 1 or less than 1. It depends. And what does it depend on? Well, if c is going to be big, then in order to get c to be big, that says that ti had better be big, or kc had better be small. So to get this to be big, the way to make it big is to make ti over kc big. So what does that mean? Ti over kc big, let's look at that. Ti over kc, that's exactly the coefficient of what controls the integral control. So the inverse of that means kc over ti has to be small. That means a not aggressive integral controller. That says if the integral controller is weak, is not aggressive, then I'm more likely to have c big, and therefore for it to be overdamped. So you can see what happens if I make kc over ti bigger instead of smaller, then I make c smaller. And as c gets smaller, I get more and more underdamped. I get more and more oscillations. And you could imagine that I could get to situations where maybe in this example, I'm not going to get unstable, but it's certainly much more oscillatory. It's going to oscillate faster and faster. If I have a more complicated example, it could actually become unstable. So why don't we invert this? This is a very unusual example, and this is why I picked just PI control, because I can actually invert this. So let's notice that if this is a step function, so if I have SP prime tilde, if SP prime is a step, then SP prime tilde is delta SP over S. And therefore, I can note that CV prime tilde is delta SP over S times 1 plus STI divided by S squared TTI plus STI. Do I want to do this in terms of the C's or in terms of the T's and the Phi? No, I'm going to do it in the primary variable. STI 1 plus 1 over KP KC plus 1. And I want to invert that. And that's why I chose PI control, because I can actually invert that for this particular example. It's unusual that I can invert it. This happens to be an easy example, so I only have a first order process, and I only have PI control. So if I want to invert this, I'm going to go to the table. So the table, and I'm going to use the table that you have in your book. So notice that I have two terms here. I have a 1 over S times a quadratic, and I have STI over quadratic. So in the second term, the S's cancel, and it's just a quadratic in the denominator. In the first term, it's S times a quadratic. So if you look at your table in line 17, in line 17, you have 1 over S times a quadratic, and in line 15, you just have a quadratic. 1 over a quadratic. So line 17 and 15. So we can actually get the inverse. So I've got a delta SP, and that's going to, so let's look at the first term. The first term is the 1 over, so that's exactly line 17. So I have 1 minus, this is 1 over the square root of 1 minus c squared. Well, c, we said, is this thing, so I don't want to write it out. 1 minus c squared, where c is equal to this, times e to the minus c over t2. Over T2. So here we have T2, which I can write that out. That's the square root of TTI. Times the sine of the square root of 1 minus c squared divided by T2 plus phi, where phi is the arctangent. I'll get into that in a second. So this is, so here where phi is equal to the arctangent of the square root of 1 minus c squared over 2. Now that's, of course, the first term. In the second term, I have plus a ti times. So here the s's cancel, and I have ti divided by a quadratic. That's line 15 with a is equal to 0. So with line 15 with a is equal to 0, I have the square root of c squared minus something times a plus 1. So a is 0, divided by 1 minus c squared, times divided by T2, where T2 is the square root of TTI, times the sine of the square root of 1 minus c squared over T2 plus phi prime where phi prime is equal to 0, because there's an a in there. Yeah. Phi prime is equal to the sine inverse of 0, which is just 0. So this just drops out. Okay, so there we've done the inverse. And that's sort of a miracle. That's because this is a simple example, we can do the inverse. And so let's just look what happens as t goes to infinity. So this is for proportional integral control. So let's look at the limit as t goes to infinity. And we can do this 2 different ways. We can do it by the final value theorem. So this is the limit as s goes to 0 of s cv prime tilde of s. So let's do it directly from here. If I multiply by s, and then I take the limit as s goes to 0. So I multiply by s, this drops out. I take the limit as s goes to 0, I get a 1 in the numerator, this is 0, this is 0, and a 1 in the denominator. So this thing just becomes 1, and I just get delta SP. So, and that's actually what you want. When you change the set point, you want the control variable to go to the set point eventually. That's it. So there is an offset, but this is a good offset, because it's an offset from the initial condition, not from the set point. We can also see that directly from the inverse, because did I leave an exponential out here? There was an exponential as well. Yeah, I left out the exponential. E to the minus t should be a t, and I see a c. Oh, ct over tau. E to the minus ct over tau. And it was the same thing here. There was a c here. And they should have been e to the minus ct over root tti. So we can notice that both this term and this term, as t goes to infinity, these are negative exponentials, so these 2 terms go to 0. and the only thing left is the 1, so I get a delta SP. So that's kind of neat. That's exactly what I want. And the reason for this is because I had the integral control. What would have happened if I didn't have the integral control? If I didn't have the integral control, I wouldn't have had the STI. Had I not had the STI, it's like dividing top and bottom by STI. Had I not had the STI, what would have happened? Well, that would have said that this term and this term didn't exist. So these two terms would not have contributed. If these two terms would not have contributed, I would have just been left with this. So if I multiplied by, if I turn this into delta SP over S and multiplied by S, I would have a delta SP times the limit as S goes to 0 of this, which would have been KPKC over 1 plus KPKC. So without integral control, and we did this before, only proportional, then CV prime of t, the limit as t goes to infinity, would have been delta SP times KPKC divided by 1 plus KPKC, which is not equal to delta SP. It would have been an offset. This is with only proportional control, without integral control. With proportional control, I actually get delta SP, so the offset goes to 0. And again, I want you to notice that, okay, so I get the right answer with a proportional integral control, but I have this issue of will I have it overdamped or underdamped? And again, I can't tell it whether this is greater than 1 or less than 1, which decides overdamped or underdamped. That, of course, depends on whether this is greater than 1 or less than 1. But that depends on the value of Ti and Kc. And you can see that when Ti gets big or Kc gets small, then C gets big. So that's good. So that means I'm more overdamped. So when the controller is not too aggressive, then the situation's overdamped, but it can take a long time to get to the answer, to get to delta SP. When I make the controller more aggressive, it reacts faster. But if I make it too aggressive, it overreacts, and I get oscillations. Again, this is unusual that I'm actually able to solve this exactly, but it still was worth doing because you can see explicitly what's going on in the solution. Notice there is, in this case, there is a phase lag, that's phi, from this term, not from this term, because phi prime was 0. This ended up being 0, but phi was not 0, if I'm not mistaken. Phi in line 15. No, I'm sorry. Phi in line 15 was also 0. There's an A. This was A over tau. A over T2, so this is also 0. So this is also 0. There is no phase lag. They're both 0. So we found that this was the arc tangent of 0 and this was the arc sine of 0. They're both 0. So there's no phase lag in either one. But you notice that you can have this oscillation. And when do you get the oscillation? You get the oscillation when C is less than 1. When C is less than 1, then you have the sign of a positive quantity. When C is greater than 1, then you have the sign of a negative, of an imaginary quantity, which ends up giving you the exponentials rather than. So it's perfectly consistent with what we had before. Any other comments I want to make about that? Well, and the only other comment I want to make about that is this system happens to always be stable. It happens to always be stable because C is always positive. And because I'm always subtracting something that's positive. That is, AC, T2 squared times 1 is always positive, so that's subtracted from the B squared. That's for this particular example. And this example, and remember we said that first order systems have this inherent stability property. They happen to be stable almost no matter what you do to them. But once you get to more complicated systems, like second or third order processes, we saw that you could lose stability very easily. And you could imagine that if I were here, if I were doing this canonical example rather than this canonical example, so instead of this being 1 plus st, these were 1 plus st cubes. So when I multiply out, instead of getting a quadratic, I would have gotten a quartic equation. In a quartic equation, when I start playing with the coefficients, all hell could break loose and I could lose stability. But the quadratic is pretty simple, but once I get to a quartic, it's not that simple. Are there any questions on that? Okay, so those who came in late, a lot of people, you'll eventually want to pick this up, because it has the canonical examples, but not now, because I'm not referring to them anymore in the class today. Are there any questions on this so far?
I have a question. When you did the inversion and you applied line 17 and 15, I was looking at the tables and I couldn't, oh no, I think I see it. The S is right there. Yeah, so you have the S and then you have the S squared, T squared term, right?
X? What's an X?
No, the S. No, I'm looking at the CV term. And then you invert that whole thing, right?
I inverted this.
Yes, that entire thing.
Yes.
Okay.
So the one term gave me this term, and the STI gave me this term.
Okay. Okay.
Are there other questions? All right, so as we said, what are our goals? We want to get the control variable to the set point. And with proportional interval control, I'm able to do that. I can also add differential control. If I add differential control, instead of 1 plus 1 over STI, I'll also have another term plus STD. And we can look at the result of that. I would suggest strongly that you try that with Simulink and play with the value of STD. And you'll see that once you make TD anything but really small, things become unstable. Okay, well, one goal is we want to get CV to the set point. Another goal, and we don't want CV to be oscillating too much. It can oscillate a little bit, but you want to get it to the set point. When CV oscillates, that doesn't turn valves on and off, because that's an output. But the manipulated variable is going to start if that oscillates, then the valves are going to be opening and shutting all the time. And once you start opening and shutting valves really fast for a long time, they break. So an important goal, goals. We want the offset to 0 fairly fast. We want CV prime to go to delta SB. We want it to go to the new set point. And we don't want MV prime to not oscillate too much. So let's look at MV prime. And let's notice that MV prime, that CV prime, if there's no D. So if there's no D, then it's equal to GP, GV, MV prime. So if D prime is 0, so no disturbance, then CV prime tilde is equal to GP, GV, MV prime. And that just comes from the block diagram. Okay, but let's recall that CV prime is also equal to CV prime from here is GP, GV, GC. Over 1 plus GS, GP, GV, GC times SB prime. So I just copy that from here. Well, notice that these are just multiplied. So I can cancel GV, and I have MV prime. So therefore, MV prime tilde is just equal to GC over 1 plus GS, GP, GV, GC times SV prime tilde. You might say, so what? Well, so what is the following? Notice that the denominator of MV prime tilde is the same as the denominator of CV prime tilde. These have the same denominators. So what does that tell me? That tells me and the denominator tells me the stability. It tells me if something's going to blow up or not, and it tells me if something's going to oscillate or not. So that tells me if the denominator of CV prime is unstable, then the denominator of NV prime is unstable. That is, if CV starts going crazy, going off to infinity, then the valve is going to be either completely shut or completely open, and it's still not going to be enough. But it also tells me that if CV prime oscillates, so if it's underdamped, even if it oscillates quickly, even if it's decaying, it oscillates quickly and decays. And that's when C is very small. When C is very small, I think I probably needed a T here. Did I leave out that T? Yes, I left out the T. So the smaller C gets, the bigger the frequency is. So the smaller C gets, the faster it oscillates. So if it oscillates quickly, if CV oscillates quickly, so does MV. Even though it's decaying, in this particular example, it's oscillating quickly. If it oscillates quickly, the valve is opening, closing, opening, closing, opening, closing, opening, closing. And then it's going to break. So that's something we don't want. And that tells me that I have to be careful with not just CV, but also MV, the manipulated verb. They're both important. So, for example, let's just, if this is CV prime versus T, if this oscillates and decays, then NV prime is also going to oscillate and decay. It's typically going to do the opposite of CV, but if this is oscillating, this is going to have the same frequency of oscillation. So this could be bad if it's oscillating that quick. So we need to be careful of that. You might have originally said, if you were only interested in CV, who cares if it oscillates and decays, as long as it decays? Well, if it oscillates and decays, particularly if it oscillates fast and decays, then you could break the valve. So that's something you want to be careful of. Now, in general, when you have a PID controller, you have to choose the constants, Kc, Ti, and Td. And to choose the best value of Kc, Ti, and Td is not an analytic problem. It's not like I can solve for the best value of Kc, Ti, and Td. It's usually a much more complicated way of doing it. So what you would do today is, if you decide to use a PID controller, in order to get the best value, you would need a model of your system. You'd have to write out your model completely. And presumably, we were doing our analyses by linearizing the models. Presumably, you would keep the models nonlinear because you have a nice computer that you can solve nonlinear equations. And you would try to solve the equations for different values of Kc, Ti, and Td. In fact, you might try, if you have a good model that's analytic, trying to take the partial of the result with the partial of the error, the IAE, the integral absolute error, with respect to Kc set equal to 0, the partial of the integral absolute error with respect to Ti set to 0, and the partial of the integral absolute error with respect to Td is set equal to 0. And if you had an analytic expression for the IAE, you would try to solve those three equations simultaneously for the best value of Kc, Ti, and Td. If you could do that, usually your models are not that easy to solve. You don't have them analytically where you could, for IAE, in a way that you can take those derivatives. Although it's conceivably possible because you can solve nonlinear equations analytically today. Now, how did people do this in the old days? The PID controller was invented in the 1940s. In the 1940s, that was when the computers available were the ENIAC, which was a glorified calculator that was used in the Manhattan Project. A modern computer that you could do normal programming with didn't yet exist. Alan Turing, you may have seen there was a movie about him a few years ago. Very interesting guy. He's the one who cracked the Enigma code of the Germans during the war, so they could basically, the Allies could intercept communications and know where the next attack was going to be. But Turing was a brilliant guy. He also came up with a mathematical theory of what is computable, of computation. And those are called Turing machines. And they are based on a mathematical structure called the monoid, which if you take a class in abstract algebra, you'll learn about monoids and Turing machines. But this was all a mathematical theory. And in the early 1950s, 51, 52, 53, John von Neumann, whom I mentioned in a previous class, who was one of the great geniuses of the 20th century, von Neumann took Turing's abstract theory and he took vacuum tubes, which is what they had then for switches, and he soldered them together and he built the first modern computer. And the architecture that he used is all modern computers are based on von Neumann architecture today, which basically sets up all the switches in such a way that you can program them to do anything you want. So what am I saying? The PID controller predates von Neumann. So why did they choose the PID controller? They chose the PID controller because it frequently does a very good job if you have good values of Kc, Ti, Td. If you don't have good values, it sucks, to use modern parlance. So you have to do a good job of finding Kc, Ti, Td, and that's called the tuning problem. So finding, optimizing Kc, Ti, Td is called tuning the controller. Now, how did people do this in the 40s when they didn't have, in the early 50s? Even in the early 50s, von Neumann made one of these, but it wasn't like everyone had one in their phone or they had a laptop or they had all this. So how did they do it? People didn't have personal computers really until, the IBM PC came out and the Apple I came out, which we're talking about around 1980. So what did they do for the first 40 years? Well, they used something called an analog computer. What's an analog computer? An analog computer was exactly what you have in Simulink, is digital today. But they had these boxes. And it was a box that was a bunch of electric circuits that did each of these unit operations. So for example, an integrator, you would have a voltage coming in, and the circuits would give you a voltage coming out that integrated it. That was just the sum of integrated voltage, dt. It was another box where there were physical circuits that took a derivative. So, and all those boxes that you have in Simulink, people built, which are on the screen, people built physical boxes that had circuits that did those operations. And then what they did is just the way you hook it up in Simulink, they took wires and they hooked them up. These were like physical wires between these boxes. You want something that's 1 over 1 plus ST? They had a box that did that. They had another one, etc. So, and that was called an analog computer. So what they would do is they would take these boxes, put them in there, and they would take a knob. there'd be a knob on these boxes to change KC, to change TI, to change TD, and then play with the knobs and look at CV or look at the error. And in fact, the analog computer is the motivation for Simulink. It's just a digital version of that. And of course, the block diagrams were developed so that you could build analog computers out of these boxes. That's a little bit of the history. And they're very useful for how you think about it. Now, the idea, of course, in an analog computer is when you turn KC, the knob for KC, you immediately get the response in CV. You see what happens. Because the analog computer is instantaneous. You change the current or the voltage, and it propagates through the system. The assumption there is that when the controller does something, you see the result immediately. It's continuous control. And what you're assuming today is you're assuming that the calculation of what the manipulated variable has to do, that this calculation, the error comes in and the manipulated variable change comes out, that this calculation is instantaneous. What does instantaneous mean? Instantaneous doesn't mean it happens in 0 time. It means compared with the time scale of everything else, of the process and of the measurement, and of the process and of the measurement, and of GD, GS, GP. Notice, GP and GD have time scales in them. Compared, the time scale of the computation is much, much faster than the time scale of the process. In chemical engineering, that's no problem at all. Time scales of chemical engineering processes can often be days. If it's really fast, seconds or minutes. Today, the computational time, certainly for doing a calculation on a fairly simple model, is tiny fractions of a second. But part of the reason for choosing the PID controller was you could do calculations on such a simple model of the controller very, very quickly. Even with an analog computer, even with a slide rule, you could do it. Today, of course, it's not a problem because we have much faster computers. There's a little bit of history there. Note that in electrical engineering problems, that's not necessarily the case. In electrical engineering problems, they're dealing with circuits where the process is something electronic, and the process can respond also in a millisecond. So there they have other issues in electrical engineering. Control is more complicated for electrical engineers because the time scales for the process could be the same order of magnitude as the time scale of the computation, or even faster. So they have much more serious issues. That's generally not an issue for chemical engineering processes. Okay, so what else? There's a little bit of chit chat here, but well, as I said, the PID controller, what's good about it is it's easy to do the calculations. If you tune the parameters right, it does a very good job. And it's versatile. For many, many different systems, it does a very good job. But it's rarely the optimal. For a particular system, you could probably design a controller specially tailored to that particular system that will do better. It's just like if you go to the store to buy clothing. You can buy clothes off the rack, and if you know your size, you can find something that fits pretty well. That's the PID controller. You got to get your size right. On the other hand, if you're going to if you're getting married, you want it to fit perfectly, you go to a tailor who makes it exactly for you. And then nothing's going to fit as well as that. If you're going to a fancy fit. Okay, are there any questions on that before we move on to the tuning problem? Questions? Okay, so the tuning problem is a hard problem. The tuning problem is where we would like to get values for KC, TI, and TD to make the system behave behave as optimally as we can. And if we're stuck with a PID controller, which is not a bad situation to be stuck with, how do we find it? And again, you can't really do this analytically unless you're in that special situation where you could analytically have a good model for the integrated absolute error as a function of these things. And then you would take the partial derivatives with respect to these three values, set them equal to 0, and solve those simultaneously. Sometimes that's possible. The problem is, any given model is usually an approximation. So you can do all this work optimizing KC, TI, and TD for your model of this complicated system. And then you plug it in and it doesn't work that great. Why is that? Because every model has approximations in it. So for example, we had approximations when we assume CSTRs, or plug flow reactors. You never have a perfect CSTR, you never have a perfect plug flow reactor. So that could introduce some error. You also, another example, in this class we linearize nonlinear terms. Well, that's great as long as you're close to steady state. The minute you get further from the initial condition, it's usually what we linearize about, the worse the model is. So remember, why do we have controllers? Well, there might be a disturbance that takes me far from where I want to be, and I want to come back. When I get far from where I want to be, CV, because of disturbance, is not where I want it to be. Well, then the model, the linearized model, is an approximation. It's not doing that well. Or if I change the set point, generally I'm changing the set point not by 100%. I may change it by 10%. That may be enough to make the linearized model not that great. Moreover, we usually assume that parameters stay constant when I change things. Well, if I change the temperature, or if there's some change, a disturbance that changes the temperature, CP may change, CV may change, delta H may change. There are all sorts of model approximations in the model that make our models not perfect. Does that mean we shouldn't model? Not at all. It's important to do the modeling. But you have to maintain a little bit of humility. You have a model, it's a guide. It's not God. It's not perfect. It's not something perfect to model, and you have to always be ready that when you actually do the experiment, it's not going to be exactly the way you predict. But hopefully you get the trends right. Okay, so, yeah. All right, so let's see how we go about and do the tuning problem. So the tuning problem has, we're going to take the tuning problem, and we're going to break it up into initial tuning, and fine tuning. So what's the difference? This is board number 3, this is board number 2. Initial tuning is model-based. So as I said, we're going to do the best we can with the model we have. But then we know that the model is not perfect, so then we're actually going to go to the true system when we install the controller with KC, TI, and TD that we've chosen from the initial tuning, and then we're going to do a fine-tuning process. So fine-tuning is on the system. This is on the model. And there are going to be 2 types of initial tuning that I'm going to talk about here. One of them is called brute force. So that appeals to the guys here, brute force. Well, stereotypes. As you'll see, brute force is not a compliment. Brute force means you're doing things without thinking too much. But it's a way to get started. The other way is correlation methods. And then finally, there's going to be fine tuning. Now, there are more modern methods of doing this, but we're not going to get to those right now. Once we do the tuning, once we exhaust ourselves on the tuning problem, then we're going to move on to more analytical, mathematical techniques for analyzing stability. So we're going to look at Baudet plots, we're going to look at Nyquist plots, etc. But here, this is a little bit more practical. The tuning problem is practical. So what does brute force mean? The idea of brute force is try a bunch of values for KC, TI, TD. Calculate the integral absolute error for each, and look at which is best. Now that sounds kind of dumb. There are an infinite number of values of Kc, an infinite number of possible values of Ti, an infinite number of possible values of Kd. So how can I do this in a way that I'm not going to be sitting there calculating from now until eternity? Well, of course, people are not that stupid. They look around and they try to do things in the following manner. So let's do this systematically. The first thing we know is that it's very easy to go unstable if I make the differential controller too aggressive. So let's just shut off TD. So start by setting TD to 0. And then pick a value of Ti and fix it. And then try a bunch of KCs and calculate the IAs. And then pick the best one. So by doing that, I'm only searching one variable. I'm searching KC. Searching one variable is reasonable. Searching 3 dimensions is not reasonable. Then what you do is you change Ti and repeat. So you do this for a bunch of Ti's. For each Ti, you search KC and you pick the best one. And then what you do is you try to make a plot. So here you have KC, and here you have Ti. Or maybe the other way around. Ti and KC. And you try to plot these curves are curves of constant IAE. You hope to get plots that look something like this, where everywhere along this curve, for all the KC, Ki values along this curve, I get a particular value of IAE, equals a certain number. And the inner one is similar, but the number is a little smaller, smaller. And then you try to hone in on the point in the center where the value of IAE is the smallest, and that gives you the best value of KCTI by brute force. Now, we'll talk about how to deal with TD afterwards. But as we said, TD is very sensitive. You never want TD to be particularly big. So once you have this value, then you can start increasing for this KC and this TI, you can start increasing TD a little bit from 0 and see if IE goes up or down. Chances are it'll start going down and then it'll go up. So chances are you only can increase it a little bit from 0 and then IE will go to hell because things will get unstable. So that's how you would do things brute force if things work out in the best possible way. Are there any questions on that? Again, the model, it's not uncommon to have model errors. So once you've done this, you might then go to the real system, try this KC-TI combination. So then go to real system, try TI KC, this combination. And because there are model errors, you might try, and even this TD star, and then try plus or minus 25% on each. So you might do a series of experiments with KC star, TI star, TD star, and then you take each one of them and go up 25% and down 25%. So I have 3 choices for KC, 3 choices for TI, 3 choices for TD. That's 3 times 3 times 3 is 27 experiments. You do 27 experiments and you pick the best one. And you pick roughly 25% because typically that's the error in the model and the parameters can be as high as 25%. So that's 27 experiments. 3 cubed experiments. And pick the best. So that's how you would do, that's brute force. Are there any questions on brute force? Now, by the way, just before I do that, how do I do this? I should have done a couple of plots here. When I say pick TI, fix it, and try a bunch of KCs, for each KC, so I would look at CV prime as a function of t. Let's say it's that, for that value. And then from this, I would get an IAE. So what do? I pick, for this TI, I pick a KC. For each, then I calculate CV prime. And then I would calculate the error, or if you like, instead of CV prime, I would make this the error. I would calculate the error as a function of time. And then I would get a number for the integral absolute error. And I would do this for a bunch of KCs and pick the best one. And that's how I get 1 point on this figure. Then I would do it for another KC, another KC, etc. And then I would do that. So for this TI, I would get this point, this point, this point, this point, for example. And then I would try another TI, and I would get this point, and this point, etc. So that's sort of the mechanism of doing that. Any questions on that? Brute force is not hard to understand because it doesn't require deep analysis. It's just sort of me have a big computer, me do lots of calculations. It's sort of the caveman approach.
I'm a little confused still about the graph concentric circles.
Well, they're not exactly circles, they're some sort of curves.
You know, concentric curves, but like what does it represent? Like what's in the middle? Is that what
As I said, each of these curves is, every point on the curve has the same value of IE, which I calculated this way.
Okay.
So this is one value of IE that's pretty big. This is another value of IE that's smaller. Obviously they can't cross because they have different values of IE. This one's a little smaller, and if everything works out well, if things go well, then the center point is the best value of IE, the lowest value of IE. This is in the ideal situation. It's usually not this clean when you do it.
Okay. So but the area inside the ring represents the.
We're not worried if areas are not, that's not something we calculate, the area here.
Okay.
The area on this curve is not interesting. What's interesting here is the area under the absolute value of this curve. That's the IAE. And that gives you 1 point here.
Okay.
Okay, so these are contours. That is, for every value of KC, TI, I have a value of IAE. So if you like, you can think of this as in a color plot. For every point on here, I have a different color, where the color corresponds to the value of IE. And then what I do is I draw a line through a curve through points of the same color. And that's how I get these. Or if you like, it's a third dimension. IE is the third dimension coming in. And I'm looking at isoplines. So if you could think of the IE as coming out of the blackboard, third dimension, and then I take slices, where, and those slices give me these curves. Another way of thinking of it.
Will there always be sort of like an optimal combination that's the smallest?
No one says this has to work. You try it. There's no guarantee. Remember, parameter space is big, it's infinite. There are infinite numbers of these guys. So you have to be kind of lucky to be choosing, and from experience, you know the ballpark of KC, TI, TD to choose, so that you can have a good chance of getting something like this. Okay, so let's say I want to go with less brute force. So with correlation method. Okay, so I need some sort of general model for processes. Now we saw that processes can be first order, they can be third order, they can be second order, they can have all sorts of stuff. And if you remember, when we plotted earlier in the semester for CSTRs in series with first order reactions, and we plotted the concentration of the outlet as a function of t. So where theta is the space n tau, or t over n tau. So if I have n reactors, we plotted if I have one reactor versus T, it looks like this. If I have two reactors, it looks a little different. And if eventually it started looking like this. So this was n goes up. Where the idea here is, what I do is I take the same total space-time and I divide it into more and more CSTRs. So if I have one CSTR, it just looks like this for a first order reaction. A goes to B, and I'm looking at the conversion, or so I could look at XA versus XA versus. As I go to more and more reactors, it starts looking more and more like this. So, is that really what I was plotting? I should look up exactly what first order NCSTRs in series. So what I wanted to, and let's, so this was the response to a step input, to CA in. So the response to CA in, for first order reaction was this in one CSTR, and it took longer. If you remember, when I have one CSTR, then when I have a step change in the input, the output changes right away. But there's a break in slope. When I have two CSTRs in series, the slope is continuous, and there's a break in the second group. And similarly with three CSTRs, there's a break in the next group. So the more and more CSTRs I have, the longer it takes for the information that I have a step change in the input to be visible in the output. I have a step change in the input, it's visible in the output here immediately. But it's obviously much more muted. This was a step change. This is a change in the derivative. This is going to take a little longer to see it. This is going to take a little longer. So the point here is that when I have a nonlinear process, then there's more of a delay in what the output, that the output is feels the change in the input. So what that says is we can have a general model of any process as a plug flow reactor followed by a CSTR. Or the other way around, or a CSTR by a plug flow. So the fact this delay is essentially a plug flow, is a delay, followed by a first order reaction. a first order system. Now, why is that? Again, the motivation here is that if I had only a first order process, then the delay would be 0, no problem. If I have a higher order process, there's a delay before things happen. It's not a perfect delay. If I had a perfect delay, then it would look like this. But it starts to look more and more like a delay with more and more CSTRs in service. So, in other words, GP tilde, or GP, would be, we can approximate it by KP e to the minus S theta over 1 plus ST. And to make life easy, we're going to assume that it's the same as GD. So that's implicitly assuming that the disturbance is at the inlet and not in reactor 3. So both the process and the disturbance are the same. Does it have to be like this? No, this is the simplest possible case. If you have another case, you would come up with other correlations. So what we would try to do is take the real situation that we have and try to fit it to this to get 3 parameters. So fit real situation to this model to get a KP, a T, and a theta. And let's call this tau instead of T. So we want to get those values for the real process. It's not going to be a perfect fit unless you happen to have a CSTR and a plug flow reactor. Any other system, that's going to be an approximation. And then what you want to do is you want to non-dimensionalize your system. Because if you want to come up with a correlation, just as you do in all your other classes, you want to do the minimum number of experiments. So as you do in fluid mechanics, in transport, you non-dimensionalize because it groups the parameters together. So for example, if you're doing flow through a pipe, you don't vary the velocity, the viscosity, the density, and the length scale separately. You see that they come together as a Reynolds number. So any one of those is good enough because the physics of the pump only depends on that combination of the Reynolds number. So here you want to do that also to minimize the number of computer experiments that you need to do. Anything else I want to say about that? I guess we're ready to do it. Except I think I lost some pages here. Okay, so let's go through and look to see what happens. So let's look at, do I want to do this for disturbance or for SP? I don't think it really matters. Yeah, let's do it for disturbance. So let's look at CV prime tilde for a disturbance. D not equal to 0, SP prime equal to 0. So CV prime is equal to, what is it? It's equal to GD over 1 plus. GS, GP, GD, GC. And I'm going to assume that GV is a constant, and I'm going to choose units to make that constant 1. And I'm also going to assume that GS is 1. So let's write this out. So this is equal to GD, so that's equal to KP e to the minus S theta over 1 plus GS is 1, GV is 1, GP, and I need GP and GC. GP is KP, this is over 1 plus S tau. E to the minus S theta over 1 plus S tau. And now I need GC. And GC, I'm going to use the PID controller, right? PID controller? Yes. So the PID controller is KC times 1 plus 1 over STI plus STD. So notice there is a KC down here there's a controller here, but there isn't a controller here because I'm using disturbance as opposed to something else. Okay, now of course if I were using a delta SP, then instead of a GD I would have GP, GV, GC. GV is 1, GP is assumed the same as GP. So I would have this guy here as well. So if delta SP were not equal to 0, then I would have KC 1 plus 1 over STI plus STD here as well. And I could look at either one of those, two separate situations. So let's do this non-dimensionalization. Let's notice that in a situation like this, there are two time scales. There's the time scale of the delay and the time scale of the process. So the characteristic time of the system is the sum of those two. The simplest time scale to deal with is if I do something at the inlet, it's going to take theta seconds to get past the delay and another tau seconds to be seen at the outlet. So the time scale of input to output is about equal to tau plus theta. So that's my characteristic time. And also I can notice that Kp and Kc, which we say here, have inverse units. So if I multiply them together, they're dimensionless. So a dimensionless quantity, K star, is equal to Kp, Kc, is dimensionless. And my other dimensionless quantities is S star. S has units of 1 over time. So I want to multiply it by my characteristic time. So that's equal to S times theta plus tau. Similarly, my Ti star should be equal to Ti divided by theta plus tau. And my Td star should be equal to Td over theta plus tau. And of course, tau star would be equal to tau over tau plus theta. So those are all my non-dimensional quantities. Can you see the blackboard, or is there too much glare? I don't hear anything. I'm assuming if you can't see the blackboard over there, it would be a good idea to move here. We have all these empty seats. But of course, that would show that you actually want to learn. And I shouldn't make assumptions. Based on the exam and the comments I made at the beginning, it wasn't clear how much people want to learn. As I said, I'll have grades, problems 2 and 3 are already graded. That's what I made comments on at the beginning of the hour. Problem 1 I will finish grading today, and you'll get them back on Monday. Okay, so let's notice that if I multiply and divide by theta plus tau, I get S star tau star here. If I multiply and divide by theta plus tau, I get S star tau star here. Kp, Kc is exactly K star. And if I multiply and divide by theta plus tau, I just get stars there. Because when I have S times theta, I multiply by theta plus tau, that makes S star, and I divide by theta plus tau, that makes theta star. And obviously, what I would want to do here is if I don't have, if I'm not doing delta SP, I would want to multiply by Kc and divide by Kc. So I'd have one parameter here, Kc. The point here is once I have this, then I can start looking at how to do my correlations. So the correlations, again, is they try lots and lots of values for this non-dimensional level, and they try to come up with the best the best fits. And for any given problem, you would look at the correlations. So let me draw some of the results. And they have them in your book. So this is the case D prime not equal to 0, delta SP equal to 0. They also have a set that look qualitatively similar, but the numbers are a little different for the other case. And what you get is the following. So this is KP, KC versus theta star. Again, theta star is theta over tau plus theta. And then I have Ti star versus theta star, and TD star versus theta star. And let's see what these look like. So, so here is say 1.82, and this is about 0.1, 0.2, up to 1. Obviously, theta star, when theta is very big, the maximum value is 1. And when theta is small, the minimum value is 0. So this goes from 0 to 1. And what you find is it looks something like this. And the next one, this is 3/4, and this is about 1/4. And we'll explain the trends in a second. And finally, again, these all go from 0 to 1. 0 to 1. And this is okay, so let's explain the trends. Let's see what's going on. Okay, so first let's look at the beginning part. Notice the beginning part, until I'm about 0.1, KPKC doesn't change. TI doesn't change, and TD is effectively 0. Doesn't really start until later. So what does that mean? That says if there's no delay, if the delay is effectively 0, that is, I don't really have a delay. I do a change to the system, I see it immediately in the output. Then I don't need to anticipate, because I see the results immediately. So TD is 0. I don't need to anticipate. Now, why does nothing change here from 0 to 0.1? That's, of course, the 0.1 is correlation. These are correlations. These are not analytically derived. As we said, the model typically has between 0 and 25% error. Those are typical numbers of the output from the model versus the output from the actual experiment. So that says when the delay is really small and goes up by 10%, I don't trust the model enough to make changes in my parameters. So until the delay is at least 10%, I just assume the delay is 0, because I'm afraid to make changes, because I know there are errors in the model. What happens later? Okay, so if now once I believe there's a delay, but it's really small, if the delay is small, then I can start getting aggressive with my controller. That is, I can make my K controller, my proportional control, I can make it work. I want it to go up quickly. I want to have a high value, an aggressive controller, if I don't have a good delay, because I'll see the results right away. Obviously, I don't want to get too aggressive, because then I'll make it unstable. But this rises almost instantaneously, meaning, what does that mean? This is the region where I don't trust the model. But once I start trusting the model, I want to go to a high value of KC. As the delay gets bigger, the system becomes less stable. So I'm afraid to be so aggressive. Again, think of you're in the shower. You have to come to control because you love that class. You really want to get here on time. You turn on the shower and the water's too cold. If you're too aggressive and you turn the hot water all the way on, you get burned because there's a time delay. If there were no time delay, you would do a tiny turn of the knob, and you would tilt, and the water would immediately get a little hotter, and you would adjust it easily. But if you have a time delay, you turn the knob and nothing happens. You get frustrated and you turn it some more. That's a high value of AC. You're turning it too much. So obviously you don't want to turn it too much, but if you don't have much of a delay, you feel comfortable turning it more because you see the result right away. You feel the result on your back right away. So that's what's going on here. But the bigger the delay, the more careful you are about turning that knob. That's KC. So you start going down. Now what happens with TI? Once I have KP getting large, well, again, KC, the proportion controller, never gets rid of the offset. I never get to the temperature I like. So what I need is I want initially, once I am having the proportion control on, I also kick on the integral control to get rid of the offset. So I get where I'm going. But again, once things are too aggressive, once there's a long delay, I can be too aggressive in the integral control as well, as we saw. When the integral control, when I make TI over KC small, when this thing gets too small, TI means a short reaction time for the integral. Too short, then C goes down. Even for a first order system, it starts to oscillate. For a non-first order system, it becomes unstable. So that's why this thing decays. Now, when I have, how about TD? When I have a situation where there are no delays, there's no delay, theta 0, I don't need to anticipate. As soon as I turn the knob, something happens. I don't need to anticipate. However, when I have big delays, then just as I go in the shower, it's too cold, I turn the hot water, nothing happens. Well, if I keep turning, I'm going to get burned. It would be nice if I could anticipate that the temperature went from 50 degrees to 51 degrees really quickly. I don't feel that on my skin yet, because 51 is still too cold. I would like it to be 80. But the differential controller could say, wait a second, don't go turning it so fast, because it went from 50 to 51 in a fraction of a second, so it's going to go up. Don't be so crazy by turning it too much. So that's the differential controller you're anticipating. But once the delay gets too large, then if the delay is too large, you might not see that change from 50 to 51 right away, because there's a big delay that may come later, and you may just be seeing fluctuations. And then you may be reacting to fluctuations that are meaningless. So therefore, you want to turn TD off. And notice it never gets too big. It never rises to anything near its potential. So those are the physical reasons for the shapes of these curves. And if you go to the case where there's a change in the set point and not a disturbance, the shapes of the curves are the same, but the numbers are slightly different. And they're in your textbook. Of course, everyone has a different version of the textbook, so it's on a different page. But you can just take a look and you'll see it. So, what would we like to say here? Okay. Anything I left out? Yeah, the only thing I would say, why did we turn this on? Because as theta goes up, as the delay goes up, we're turning the proportional controller off. So if the proportional controller isn't doing anything, we need to start anticipating. Notice as this goes down, this goes up. Because as we're avoiding being too aggressive with the proportional controller, we need some control, so we start anticipating. But eventually we can't anticipate anymore. Any other comments? The other thing to notice is This has a fairly small range, TI. It's easy to make TI too small. You make it too small, things are aggressive. You make it too big. Actually, let's just look at that for a second. I think I explained TI upside down, so let me go through and redo TI. So if you remember, TI let me really re-explain TI. Remember, when TI is small, things are aggressive, not when TI is big. But TI isn't alone, it's KC over TI. So the reason this is, when the proportional controller goes on, then TI is turned on, but it's less aggressive. Because what we're doing here is we're letting the proportional controller do the work, and eventually we want to make sure that we get to no offset. So by moving up here, the integral control becomes less aggressive. So it just takes care of the long time. It says short time, we'll leave it to the proportional controller. But at long times, we'll take over. And notice we're not detuning it that much because it's multiplied by KC. So by this going up, we're keeping the integral controller working because it's KC over TI. That's the strength of the integral controller. So this going up doesn't mean we're turning off the integral controller. It means we're just trying to keep it still working because KC went up, so we have to raise TI. And similarly, here, as the KC goes down, when theta goes up, we don't want KC going down to turn off the integral controller, because the integral controller is KC over TI, its strength, KC over TI. So we decrease TI along with KC, so we're still taking care of the offset. So that way the ratio is staying pretty much constant. So this guy is more or less a slave to this guy to keep the integral controller working and to make sure we don't have offset. Okay, so a couple of rules of thumb, and then we'll have to leave the fine tuning to next time. And we'll actually do an example next time. But a couple of rules of thumb before we finish. So what's going on here? As theta star goes up, as the delay goes up, the controllers detune. The controllers get less aggressive. Particularly the proportional controller becomes less aggressive. And basically because when you have big delays, you want to slow down the reaction of the controller because it's easy to overreact. Now really, all three parameters have to be tuned together. It's not like they're independent. They really depend on each other. But these are correlations. They're about as good as we can do right now. And obviously, the GP and the GD, the actual model we choose, if we choose a different model here, we're going to get different correlations. So these are for this particular simple model. But it can be shown that, what does it say? That the tuning is fairly insensitive to the type of disturbance. Once you have the G's, notice all we did the tuning based on this GD. We didn't really worry about the D prime. So I need this D prime tilde. I didn't even talk about the D prime tilde. And that's because you can, by trial and error, and you can also show it, that the values of your constants don't really depend on D prime. They depend much more on this G, on this set of G's. That's not obvious, but that seems to be the case. And finally, the more noise you have in the system, the more you want to just turn TV off, because you don't want to be reacting to noise and to fluctuations. So that's sort of a general trend And if you have a system with a lot of noise, then you want to redo the correlation. And they give you other charts in the book where you set TV equal to 0 and you redo these two curves. So it's going to be slightly different if you don't have a TV. So that's the situation there. So what are we going to do next time? We're going to talk about how to do the correlation method for a particular example of 3 CSTRs in series. We'll talk about this. We'll talk about fine-tuning, how to do the fine-tuning. That is, from your initial tuning, you then go to the system and you try to adjust these values, the fine-tuning. And that will more or less get us to a point where we can finish that chapter and we'll start looking at more analytic methods. Are there any questions? And I will give you a homework today. Again, you will get, I graded exams, problems 2 and 3. I'll finish problem 1 today. I made comments which you could look at on the video at the beginning of the hour about the results of problems 2 and 3. The take-home message was there were issues with 228. Many people never really could write down an energy balance correctly. I had 2 tanks in problem 2. A lot of people didn't realize that 2 tanks means 2 energy balances, not 1. And that tank 1 had a heat exchanger, tank 2 had a reaction. So tank 1 doesn't have a reaction, tank 2 doesn't have a heat exchanger. By that, I've taken care of more than half the class that got the energy balances wrong. You really can't do the analysis right unless you start. And a little words and whys for the final. When I grade problems and assign the points, more of the points are at the beginning of the problem than at the end. Even if you have a lot of calculations to do, your bang for the buck is to get the beginning of the problem right rather than the end of the problem. You have to choose one. Make sure you start the problem correctly because you'll get a lot of points. Like problem 2, if you had just written down the energy balances correctly for the 2 reactors, you already had 12 points. Just writing the energy balance correctly, 12 points. And then if you got the Q, the form right from the textbook for what the heat exchanger value was, that was another 5 points. So you had 17 points by writing the first 3 equations, which should have taken more than 3 minutes, especially since one of them was copying out of the textbook. Out of 40, you had almost half the points. Instead, people would rush and write the wrong energy balances, and then get lost in the algebra with the Laplace transforms, which later on in the problem, lots of calculations were worth 2 points, 3 points. So they got those calculations wrong anyway because the initial problems were, the initial balances weren't right. In any problem on any exam, start the problem correctly. It's worth starting it correctly. You'll worry about the details later downstream. And the other comment for problem 3 was 3A was in the homework. The TA solved it during the session, the review session, and posted the video. And still, fewer than half the students in the class got most of the points on 3A. I don't understand that. Okay, finally, if anyone wants to see the solutions to either exam and how the points are divided, just make an appointment with me. You can come to my office and you can sit there and read them as much as you want. You just can't take pictures. But you can certainly sit there and read them. It's not a problem. It's not a military secret. You're welcome to see. And again, if there's anything you don't understand, you're welcome to ask me. Enjoy your Thanksgiving. Anyone who didn't get this page at the beginning, which was the canonical examples?
Professor.